Who is your advisor? Who?
Tracy.
Wilson? Yeah, Tracy Wilson. Okay, yeah, she can talk with the that person too. There's a fair chance, I'd say more than a 50-50 chance, probably see Miss Tubbs on Friday. So if you wanted me to say something to her, I'll be glad to. I mean, we get along fine. We're just very congenial, so I can just say something.
Because I still haven't figured out all my classes yet.
Right.
So once I get all my schedule done, I'll...
Okay. Just a couple of things. You're a pre-engineering major, is that right? And you've got your degree plan? Or you're familiar with that? Now, the only reason I know this, the last person I advised, and that's the other thing, I've been advising students all week too, and times when I could have been working on something else, but I've been advising students. The last guy I advised, I think it was yesterday, he was a pre-engineering student, and there's something squirrely about the way they've written about him. Here's the background. Area 1 has the 2 English compositions. Area 2 is humanities and fine arts. Generally 12 hours are required there. Area 3 is math and sciences, usually 11 hours there. And Area 4, it used to be, and it still is for most people, 12 hours there. Now there's a connection between Area 2 and Area 4. It says you can take 1 literature and 2 histories, or 2 literatures and 1 history. But for engineering majors, in a lot of the engineering curricula, they have cut back, sometimes in Area 2 and in Area 4, and only want 9 hours each. Okay? Now, the guy I was advising yesterday, I believe it was, he had taken his 2 history because they only wanted to take 1 literature. But they had cut back the Area 4 requirements, and now what's listed, even though they still have that listed, what is listed now says 3 hours of history and 6 hours of social behavioral science for the 9 hours. And he had already taken the 6 hours of history, I think before they made the change, but they still changed it. So I said, I can't answer this now, but it may be they're going to require you to take a second social, 2 social science. That's what it says, 6 hours here and only 3 hours there. So just because it says that you have that option on the history, down here you don't have that option on the history. You only have 1 hour, 1 class of history, so that means take 2 literatures. But I would go back and look at the degree plan carefully and see. Have you already done the history? Oh, you haven't. So you're just needing to do any old history.
Yeah. I'm going to do the U.S. history.
You want to do U.S. Yeah, I think I noticed that too. When I looked at that, it looked like they were all, or mostly world history and Western civilization. I don't remember. I didn't look on both campuses, but I didn't remember seeing many U.S. histories out there, which is too bad. So yeah, if it could be that the instructors that like to teach U.S. history may be taking the summer off or something like that, and people who like to teach civics and Western civic and world history, they may be the only ones teaching this summer. So I don't know, but I can check with you. You're wanting, and it doesn't matter which one you take, 201, 201 or 202. Okay, you printed the whole thing again, right?
Yeah, the main page.
Right, I see it. Thank you. So you can take either one. So if either one of them are offered, you can do that. It's not something you have to do in sequence. One is early American history, and one's later American history. You don't need one to do the other. So don't let that be a bother. But also check that other thing. So even though they say the other thing, if your area 4 says 1 history and 2 social sciences, then be sure that's what you do, so make sure you get your second literature up there. Does that help any?
Yeah.
Okay. All right. Yeah, we are recording. I couldn't remember if we got that lit off or not. So let's do the slideshow from current slide. Now let me go over, oh wait. Let me also do this. should have done this before I turned on Screencast-O-Matic. Okay. Now, test 1. Did I already return your test 1 to you? Yes, I may have. Okay. I was going to say, I don't see it in here. I think you were absent that day. So here's your test 1. Okay. What you just turned into me, was that test 2?
That was when you're out.
That was when you're out. Yeah.
But I had already turned in test 2.
You have, yeah. I've got it marked but not graded, so sorry about that. Kept thinking I'd have some time today to do that, and I haven't. I got the correct and incorrect, but I haven't tallied the score yet.
If you want to give me 100, that would be fine.
Okay, if I want to, I will. Okay, and if I don't want to, no, okay. Okay. You're very kind. So don't leave. Oh, I stayed late last night making up the test. The Silver, you got yours already, but on 3 different pages. I've got one for you on 2 pages. Same questions, but all the copiers were closed by the time I finished, so I slid it under the door to be copied. And this morning when I came in, she hadn't copied it yet, and I haven't been able to get back by the copy room. So at the end of class today, don't leave until I go down to get the copy of the test. Okay? Because she should have copied them by now. She was doing something else this morning, so I didn't get to ask her. Okay, so now how about student course evaluation? Y'all done them yet? Yes? And not yet. Okay, no problem. Just get them done before the end of the term. Don't forget. All right. We have classes as regular today. We have this class, differential equations, and then I have my office hours 3:15 to 5:15. I'll probably be here late again tonight. I've got so many papers to grade, but I don't know how long the mind and the body will hold back. At some point, I'll leave after 5:15. Maybe not right at 5:15. Okay, tomorrow classes is normal, and then. However, I'm guessing my physical science class tomorrow, we may actually finish before 5:45. So I may have, but my office hours tomorrow are 10:45 to 1:15. Okay, then on Friday, I have one little issue. My wife has professional meetings, poor gal, in Amsterdam. So she'll be flying out Friday. And normally I'm on Birmingham campus 7:45 to 1, but this Friday I got to leave early to get her to the airport. And like I said, I've put in enough hours late this week I can take off an hour early. So I'll probably leaving 12 or 12:15, somewhere in there, so I can get home and get her to the airport. So my office hours have changed just a little bit on Friday. Now, I'll give you the test today at the end of class, and then at that point, I will be, you can turn it in to me anytime. Now, I think both of you have turned in your papers, right? Yeah, in this class, just one person hasn't turned in the paper. And I still got to get your second test. Some of you have turned it, but not everybody. And then, so before we leave today, I'll give you your last test. So please, so if you finish that test, as the manual did for its linear algebra, which was so hard, if you finish it today, I'll take it anytime today. I don't think that's likely, but you can. I will be here all day tomorrow, even though I'm in class. So if I'm in class, you can slide in under my door. My office door is 265. That will be fine. But I'm in class, regularly tomorrow. Friday, I'll be on the Birmingham campus, but if you finish your test and this is more convenient for you than Birmingham, you can slide it under my door here, no problem. But if you're on Birmingham campus, anytime between 7:45 and 12 tomorrow. Don't come by at 1 tomorrow and think you can catch me on the Birmingham campus. You won't. And don't leave it over there because I won't be back there until the following Friday. So,
Where on the Birmingham campus are you?
Do you know where Dr. Pruitt's office is? No. Do you know the B Hall?
Yeah.
Long academic building. Okay? The end of the building toward the gym and the tennis courts and baseball field. Right? Okay, you know, there's actually two levels for the building. There's a lower level and slightly upper level. You go up half or down half, you know. Go up half. So if you come in from the gym, baseball field, tennis court side, when you get to that top step, the door immediately to your right is 122. If you come from the other end of the building, go all the way down till just before you get to that top step is the last door on your left, B122.
Well, it depends what time. Yeah, I got you.
Yeah. So you got a general picture of it. Where were you giving him? The STEM lab?
Dr. Wilson's.
Oh, Dr. Wilson's office. Okay, yeah. Yeah, hers is in that lab. Right there. Then you come out of that door, and if you went straight, you go down a short hallway to go to the C building. Veer right, slightly to the right, and that door right there. And you'll see Dr. Pruitt, you'll see his secretary is Rose Saxon, you'll see their names there. That's the office. When you go in, the Saxon's desk is right there. She's a secretary or administrative assistant, whatever they call it. And then behind her area there is a copy room, and that's where I go on Fridays. Okay, there's a table place for me to work. The big corner office, that's Dr. Pruitt's office. The big corner office. Okay, so got an idea. Okay. All right, now where we left off last time, I think we. Oh, let me turn on the projector. And I marked the roll already. Oh, let me finish about. So you can turn in the final anytime this week or next week. Okay? Let me give you generally what I'm going to be doing next week. No classes next week. Well, no, that's not quite true. Okay. Mini-term classes continue next week, but not full-term classes. So on Monday, my Monday classes, all four of my Monday classes are take-home tests just like this one. So I'm not going to be up here in the classroom unless someone comes by to do a makeup test. And if they do, I may be here, but the odds are, here's what I do when someone comes in to do a makeup test. I look for the classroom closest to my office that's free, and that's where we do the makeup test. That way, when I have to go back and forth to the office, I don't have to walk as far. If the phone rings, I might be able to hear it and get to it before it quits ringing. So I usually try to do 263, 256, 261, 254, 259, or even 257, or here, okay? If I get up here, I'll probably come here. But if I'm not in my office, look for me in any of those classrooms on Monday or Wednesday. My hours Mondays and Wednesdays, 7:45 to 5:15, just like normal, okay? Now Tuesday morning at 8, I have a final in this room. That's from 8 to 10, basically. That class typically takes a little longer to finish because it's a bigger class, so I may be here a little past 10, but I'll either be in my office or here, somewhere in between. So that's 8 to 10. Tuesday afternoon at 1:15, I have my regular physical science class. Now, I don't think we'll go as long, but it starts at 1:15, and then it'll go, I'm guessing we'll be through 3, 4, or 5-ish, somewhere in that time frame. May not be. We may go to 5:45 as normal, but I don't think so. Okay, so that's Tuesday. Wednesday, just like Monday, I'll be in my office unless I'm doing a makeup test, and that's 7:45 to 5:15. But then Thursday, I don't have any finals in the morning, so I'll be in my office or some room in between if I'm doing makeup tests. And then at 1 o'clock or 1:15-ish or sometime in there, that's when the final is scheduled for the physical science class. Now, if you start looking for me and can't find me, go to my office, because I'm giving those students, let's see, there's about half the class is automotive students, and this is their last term here. And many of them are from out of state, okay? I know some are from Mississippi, some are from Florida, and all over the state of Alabama. So they're always begging me to, hey, I've got a long way to drive. We have to go to 5:45. I said, don't take as long as it takes. So I know some of them trying to get home, and this is probably their last final. So what I'm doing, I'm letting them come in anytime next week after we finish the material and take the final early if they want to. So I can't guarantee you there'll be anyone taking a final at 1:15. So if you come looking for me and I'm not here, it's not like I'm disappeared. It may be everybody finished the final early. Now, about the other half of the class are career tech students, and they want the whole week to study. They may have finals otherwise. But those guys that live out of state, actually, I'm sure they're going to want to get home as soon as they can. So if you don't see me here at 1:15, check my office. But that's technically when the schedule is scheduled, and I'll probably be here. But if students finish, then I'll be back in my office. Okay. And then Friday of next week, I'm on Birmingham campus, 7:45 to 1 o'clock. Now, if you do come by sometime and I'm not here, you can slide whatever work you've got under my door in 265. Be sure you go to my office door, not the classroom door. And I will pick it up the next day. Even if you do that on a Friday, I can pick it up Monday and still get it graded in time. But I'd like to have everything in. Now, I'm preaching to the choir here, but the one person who hasn't turned in a paper, if it's not in today, you're going to start losing points. Okay, but the rest, the other tests and everything else, get that into me as soon as you can. I'd like to get everything in next week, so I do have Monday, Tuesday, and Wednesday till noon to get your grades in. So that's plenty of time. So if you get me the stuff by the end, let me back up on this too. We have a niece graduating from Auburn next Saturday, but it won't interfere with anything. We'll leave Friday evening to head down there, so that doesn't mess with anything. But the following week, and are you graduating? Yeah. Okay. Okay. The thing is, I probably won't be at graduation because we have a nephew graduating at LSU that weekend, and we're going to have to leave on Thursday evening, sometime Thursday, to drive down there, and then his graduation's on Friday, and we'll be driving back on Saturday when y'all are graduating. So I won't be at the graduation, I don't think there's any way I'll be able to get back in time. You're not going through the circuit, okay. Well, I'm not either. Okay, so are you doing anything like honors college or anything like that? Yeah, but I mean, are they doing anything special for graduation? Okay. I know the ambassadors have to be there. I didn't know if honors college people did. I didn't think they did. Okay, enough of that. So that also contributes to the fact that I won't be here Thursday and Friday of next week, or at least parts of Thursday and none of Friday next week. So if you do turn in anything, slide it under my door. I've been forgetting to tell other classes that. Okay, any questions? That may not be right either. Yeah, that's right, yeah. No, I mean, I'll be here next week. It's the following week I won't, so y'all don't even care because y'all won't be turning anything in, please, that late because I've already had grades turned in. Never mind. Okay. Oh, boy, let's get started. I believe we beat this slide to death last time, talked about it. So let's move on to the definition of a double integral over a rectangle. Okay? Now this almost looks like a huge jump from what we were doing, but it really isn't too bad. Okay? Basically what we do, if we have an integral, they're talking about double integral now, that means you have two independent variables, f of x, y, independent variables, over a rectangular region R. Okay? Usually if it's three-dimensional, they call it D for domain. Rectangular region R defined by this limit, the double integral over that rectangular region, f of x, y, dx. You're integrating this function over that. Well, how we do that is the limit as your partition. That's what the P stands for, your partition. Remember, as you let them get smaller and smaller and smaller, more and more often, as that partition is going to 0, and then it's a double sum. First, you're going to sum over the j's from I1 to m of alpha Pij. That would be all the points in those partitions, intervals there, times the delta dA, which is the area of that partition. And that's, of course, going smaller, smaller, smaller. And then secondly, you integrate for the i's from 1 to n. That's the other side of it. If that limit exists, we say that alpha is integral over that region R, that rectangular region R. Not a very useful definition, but that's what we mean. It's the limit of a double Riemann sum, basically, or something like a Riemann sum. Okay. Okay. Here is a region R. Now, the region that you're integrating on is just this region here. From here to there, to there, to there. That's the rectangular region. X is going from, now since this is positive x here, from minus whatever this is here to positive whatever it is here. Your y is going from minus, because this is positive this way, minus whatever it is here to positive whatever it is there. It doesn't have to, it could not include the origin, but this one that we're doing, that's what you're integrating with. Your function, alpha of xy, is this thing that's in here. Now notice here, at least my perception of this is above that plane, and this part is below the plane, and the part back there is below. This is above. So it's the signed volume, some of this is positive, some of it's negative, of the region between the graph of z is equal to alpha of xy and that rectangular region R in the xy plane. So that could come out very close to 0, negative, or positive, depending on whether this volume down here and over there is greater than or equal to here. They didn't give us a function, they just showed us a picture. So that's what your double integral is doing in space. Okay? Now, and in the text, you'll see they split that into, let's say it right, a V1 over here, a V2 over here, a V3 back here. I don't know why they chose a V4 here. These two positive volumes, those two negative volumes, and add them together, and that's what you get. Okay. Now, in computations, we often assume that the partition P, that little, oh, you don't see it on this slide, it was on the previous slide, the funny looking P is regular, meaning that the intervals A to B and C to D are each divided into subintervals of equal length. In other words, the partition is regular if delta xi is equal to delta x, always the same, and delta yj is equal to delta y. And in that case, then, let me go back a slide. Okay, well, no, they've not introduced that yet. Okay. Goodness gracious, where is a figure that has these things on it? Wow. I'll write them on this one. Your delta x then would be now the x. Goodness gracious, this is such a pain in the neck. Remember, the x was going from A to B, and the y was going C to D. So this would be b minus a, that's the total length of it, divided by the number of intervals, which was n. And your delta y is equal to d minus c over m. Okay? And because you're going to make each one of them the same. It's not that we do this one this big, that one that big. You know. Some of the early illustrations were like that. Now we're going to make them regular. Okay. Now, for a regular partition, the absolute value of that is going to tend to 0 no matter how you split it up. So therefore, as n or m tends to infinity, you certainly see that would be the case here. So let's do a double integral. This doesn't quite look like the picture in the new edition, but I think it's basically the same thing. Okay? Maybe not, we'll see. Let R be the partition, the rectangle, 1 to 2.5 on X, and there, well, let me blow this up a little bit. Okay. From 1 to 2.5 on X, and from 1 to 2 on Y. Okay? So you see it's a little bit wider on X than it is on Y. That's okay. It says calculate the S, which is the, goodness gracious. The Riemann sum, okay? Calculate the Riemann sum S 3, 2 for the integral, and 3 is what n is, and 2 is what m is, okay, for the integral, okay, using the following choices of sample points, okay. Your function is z is equal to xy, okay. So we're doing the Riemann sum S 3, 2, okay. So if you look back above, that's, or on the let's see, the previous page on the top of page 822, it lists it, and basically almost the same. Actually, that one. Okay, Marcus is here. All right. Let's see. I do have, I think, a test for you. Now, and by the way, I think I may have mentioned. No. Did I already give you your test one? You did. I did. Okay. Yep, there it is. Okay. So basically, if you go to the top of 822, that's the Riemann sum that we're talking about. I've got to shrink this back. S sub 3, 2. 3 is equal to n, and m is equal to 2. Okay, great. Thank you. I'm sorry?
Did you get that fine?
Yeah, I have it. I was going to give it to you at the end when I explain what to do and what not. Okay. This is equal to the sum, and they do the delta x's first, okay. I equal, well, they do it last actually. Sort of wish they didn't do it this way, but they do. 1, 2, and your n is 3, and your second one is j equal 1 to 2, and it's your f, which is your z, which is xy, so it's x sub I, y sub j, okay, then delta xi, delta y, j, okay? Yeah. Now, I went on and put in what the function was, and the function is the product xy. So let's do them. Now, they first say, do it with the lower left vertex. Okay. Now, x is divided into 3 parts, so that'd be 1, 1.5, 2, and 2.5. And your y is 2, that'd be 1, 1.5, and 2. Okay, so the lower left vertex would be then this point here. 1, 1 would be your first one. 1.51 would be your next one. 2, 1 would be that one, and 2.51 would be that one. The next one would be 1.5, 1, no, 1.5, 1.5, and 2, 1.5. Okay? Those will be your 6 points. 3 by 2 is 6. So, that's what we're going to do. So, your first is going to be 1 times 1 times, now your delta x, by the way, is 0.5, and your delta y is 0.5. Back to what we did before. B minus A in this case was 2.5 minus 1 over 3. That would be 1.5 over 3, which is 0.5. And your C minus, or D minus C is 2 minus 1 over 2, which is 1 over 2, which is again 0.5. So this is very regular. So your delta xi is 0.5. And delta yi is 0.5. Okay? So there's your first. The next one is going to be, so it's going to be plus. And it doesn't matter which one you go through. We can do the j's first. The next one will be, the x will be still 1s. And it'll be 1 times 1.5 times, let's go on and multiply that, 0.25. It's going to be the same on every one of them. Plus, and the next one will be, yeah, we're doing the j's first, so that's right. Next will be 1.5 times 1 times 0.25 plus I may have written them backwards before. Yeah, no, that's okay. 1.5 times 1.5 times 0.25. Next one would be 2 times 1 times 0.25 plus 2 times 1.5 times 0.25. Now, if you notice, every one of them is times 0.25. So let's just take that out. I'll make it 1/4. Be a little easier to write than 0.25. Okay. And then it's going to be 1 plus 1.5 plus 1.5 plus 2.25 plus 2 plus 3. Right? All right. These two add to be 3. 3 is 6, and 2 is 8, and 1 is 9. That's 11.25. So 0.25 times 11.25. Someone multiply that and see what you get. They did it all in fraction forms, which is fine. What do you get? Anyone got it? 2.8125. That's exactly what they did. 2.8125. So they did it in fractions and wrote the answer in decimals. I don't know why. Okay. But the next time, that was using the lower left corner of each partition as our point, okay? Now we're going to use the midpoints. Now the 0.25s are not going to change, so all we got to do are the midpoints. Now the midpoints on these, what I'm going to do is expand this. Okay, 1, 1.5, 2, and 2.5, 1.5, and 2. Okay, I didn't need to put a 0, but anyway. So here is your grid. The midpoints are right here. What we did at first was the lower left. Now we're going to do the midpoints. Now these midpoints are a pain in the neck because this is 1.25, 1.75, and 2.25. And this is 1.5 and 1.75. So basically you're going to multiply your x and y's there. Okay? So, why don't you folks with handy dandy little calculators do this. You can start out with 0.25 if you want to, times, open parentheses, and multiply these. 1.25 by 1.25. I thought for sure I wrote it down. I didn't write the 2 in there, that's why. Okay, so 1.25 times 1.25. Thank you, I don't want to do this in my head. Okay, not that I could. Okay, 1.25 times 1.25 plus 1.25 times 1.75 plus 1.75 times 1.25 plus 1.75 times 1.75 plus 2.25 times 1.25 and plus 2.25 times 1.75. Yeah, you add all those together and then multiply by 0.25. Did you get them? I know I was saying them too fast. 1.25 times 1.25 plus 1.75 by 1.25 plus 2.25 times 1.25 plus 1.25 times 1.75 plus 1.75 times 1.75 plus 2.25 times 1.75. Add them all together and then multiply that by 0.25. Should be 600. Talking too fast, yes. Calling you millennials, you're supposed to be so fast with the thumbs, you know, right? I talk too fast. I don't know why we do this anyway, but they wanted us to. By 0.25. Same as we did there.
3.9375.
That sounds reasonable. Let's see if that's what they got. I think I need to be on the next page. 3.9375, exactly. 3.9375. Now, which of those do you think is probably closer to the actual volume under that curve over that rectangle? The midpoint certainly will be. Okay? In fact, that's probably not too far from it. In fact, let's just do it. Let's do the actual double integral. Not supposed to do this yet because you're not supposed to know how to do this yet. Okay? It's x times y, and that becomes a dx, this becomes a dy. That's what it ultimately goes to. Now, rather than saying over a region, we split this. Now, here's the place that's important. And it doesn't matter which order, but since I wrote dx, dy because they had delta x, delta y, then I've got to do the x's first. So x is going from 1 to 2.5. The y is going from 1 to 2. You see the way it broke it down? Now, here's how we do that integration. Let's do the inner one first, and we only integrate the x. We treat the y like it's a constant, just like we did with partial derivatives, right? This is kind of undoing that, okay? Not quite, but kind of, okay? So in other words, you could pull the y outside and put it with that integral. So let's do that. That'd be the integral from 1 to 2, y times, now let's do this integral in here, antiderivative of x dx. So I pulled the y out there. All you're left with is the antiderivative of x dx. What would that be? X squared over 2, right? Evaluated from 1 to 2.5. Okay? And then we'll have our dy out here because we haven't done that yet. Okay? So, this will be the integral from 1 to 2 of y. Now that integral, 2.5 squared, I think is 6.25, isn't it? 6.25 over 2 minus 1/2. Okay? Then you have a dy. Is what? 2.625. Is that what you said? Okay, this number is 2.625. Okay, I'll take your word for it. All right, that comes outside 2.625 here, and do this integral. Integral of y dy is y squared over 2, and that's from 1 to 2. That's going to be a little easier to figure. And that would be 4 over 2, which would be 2 minus 1/2. Okay, which would be 1.5. Right? So 1.5 times 2.625. Multiply those. Whoa, look at that. Our midpoint gave us exactly the same value as that, right? Is that right? Okay, good deal. And that's because they were linear, okay? So everything was linear, so it did work out exactly. All right, we weren't supposed to do that last part, but we did anyway. Don't tell, and I won't. Oh, here's the pictures of those. Hopefully you'll recognize it. That was the lower left that we did first. Those are our 6 points there, and here are the points here. What you do is the x value here by the y value, x value by the y value. That's what we're doing to get our function part, and your areas there were all the same, 0.25. This time you did this, this, did all those, multiply those products, and then that across the area, which was the same. Okay. So the sample points lower left, vertices, and sample points at the midpoint. Okay. Here is example 2. Use geometry to evaluate the double integral of your region R of 8 minus 2y dA, okay, where R is, and when they write it this way, that way, or maybe a little neater than that, this is always x by y, okay, first by second. So this, x is going from 0 to 3, and y is going 0 to 4. Okay? And that was your function. Z is equal to 8 minus 2y. Okay? I didn't actually say that was a z, but that is what your upper one is. Okay? Notice there's no x dependence in that. Okay? So, you've got a wedge here, okay? doorstop, something like that, right? That's all that is. It says use geometry to figure out what that volume really is. Well, don't you see, that would be exactly half. If you took this and flipped it over itself like that, you would have, so this end is here and this end is up here. You would have a block of wood that would be 3 by 4 by 8. 3 by 4 by 8 is what? 96? Okay. I think. Huh? 3 by 4 is 12 by 8, 96, right? Take half of that, 48, right? So we think it's going to be 48. Why did they have us do that here? If they said do it by geometry, okay, it was easy. Let's do it by integration. Now, I want to point something out to you here. You can do the order any way you want to, but since this one has y dependence with no x dependence, let's take care of the y's first. So we'll do your dy's first, 8 minus 2y, dy, then do the dx's, okay? So now the order is a little more important. When it was x, y, who cared? Okay, which one you did first. Let's do the y's first. Well, y is going from 0 to 4, right? The y is going 0 to 4. That's what this says. This is y, this is x. And the x's are going from 0 to 3. By that, let's do the integral. Integral from 0 to 3. We're not going to do that for quite a while. Let's integrate the first one. Antiderivative of 8 with respect to y. 8y minus the y's are going 0 to 4. You see, we're going to do the dy's first because this has a y in it, doesn't x, so why muddy the water? Let's just get rid of the y's first. See, that's what integrating does. It takes that variable out. Okay, and the y's are going from 0 to 4, the x is going 0 to 3, z, which we're not ever going to do, it's going to 8. Forget about that. We don't even need to know that now. Actually, there the 8 is. Believe it or not. Okay. Okay. So, and did that, what was your question?
Are we integrating from 0 to 4 or 0 to 3?
Okay. Okay, we're doing the innermost integral first. And we do the y's, because I chose to do it first because it has a y in it. You could have done it either way, but then you have to change your d's and you also change your things. So you're integrating 0 to 4. So this on the outside we aren't doing yet. We're just doing one on the inside. Okay? So antiderivative of 8y is 8y. What's the antiderivative of 2y? Y squared. That we're evaluating from 0 to 4. So this is all inside here. And then we're going to do our dx. See, the other was window dressing. Okay. So, aren't ready for the 0 to 3 yet, but let's do that one. Evaluate that one. Help me out, somebody. Second? 8 times 4 is 32. Okay. Minus 16, you said? Okay. And then I can do the zeros. Okay, done. Okay. So this will be what? Integral from 0 to 3 of 16 dx. Well, guess what? We can pull the 16 on the outside if we want to. So pull it out there. What's the antiderivative of dx? X. So there'll be 16 times x evaluated from 0 to 3. I think I could even do that one, maybe. What would that be? 16 times 3. And what's 16 times 3? 48. Very good. And that's exactly what we got before. Give you confidence this double integration works? Of course it does. Okay. Does it make sense? Okay. Now, any questions on that before I move on? Okay. Here's the theorem. Since there were no questions. Okay. Here's the theorem. Continuous functions are integrable. Isn't that nice to know? If f of xy is continuous on a rectangle R, then f of xy is integrable over that rectangle R. Now notice they say continuous functions. They don't say they have to be smooth functions. If they're not smooth, in other words, if they do something here and then come down here, you may need to break it into pieces, but you can still integrate. Okay? So that's good to know. If you're discontinuous, how in the world are you going to find the volume under a discontinuous roof? You know, not going to be easy. Okay. Not only that, but here's another theorem, and this is the linearity of double integration. In basic, it's something I've already been doing. Sorry about that. No, I'm not. Okay. Is this. Assume that f of xy and g of xy are both integrable over that same rectangular region R. Okay? So, if we're integrating the sum of those two vectors, functions, over that area, dA. By the way, did you notice our dA is now dx times dy? Dx times dy, that gives you a little dA. That's what the dA stands for, that little area. Dx times dy, that gives you that. All right? What you could do, the integral of a sum is the sum of the integrals. As long as these are integrable functions, you can split that up. You can integrate over that region R, f of x, y, g, dA, add to that the integral of g of x, y, dA. Or for any constant, now for some reason these are capital C constants. All in the past it's been little c. This is capital C constant. Very good. It's just a constant. If you do the double integral of c times a function, just like I've been doing, you can pull the c on the outside of the integral and just integrate the function, then multiply by the c. That makes life a little easier most of the time. Don't you think? Okay. Oh, I hit the wrong button. All right. Now, here's another little blurb I think you may find interesting. If the c is all you're integrating, and you pull that out, then the integral of dA is just the area of that region right there. Because your height is now 1 everywhere. So it's really the volume, so c times the area. That's all we did. That's what we did on that when we pulled out that last one. Okay, good deal. Any questions on that? Okay. Now here's figure 10. For what it's worth. The double integral is the signed volume of the box base R and height C. Okay? This shows what we were just talking about. If this is your rectangular region R down here in the XY plane, and your Z is just some constant C up here, what you're integrating is that box right there, which is the area of the base times C. That's exactly what we got. Area of the base times C. The dA, area, integrate that, multiply times C. Make sense? Okay. Now, what in the world is this mess? All right. This is arguing by symmetry, okay? Okay? Use symmetry to show that the integral of xy squared, that's that function there, over the rectangular region from x, I guess both x and y are going from -1 to 1. They don't list it, but I assume that's what they're saying here. Yeah, they say R is -1 to 1 X, -1 to 1 Y. Okay? And it's that function. Then, without doing any long, involved integration, look at that thing. Okay? Number one, when I look at it, it looks pretty confusing. But, you see, on X's, everything's positive here, negative here, because Y squared is always positive. So X is negative, this product's negative, and X is positive, the product's positive. Okay? The Y, though, the vertical traces along the x-axis, when you x constant, these are all parabolic, okay? And they get, it's really a lousy rendition, I think, but anyway, they get, what I do is picture this as x is a variable coefficient, you might think of. So you're starting at 0 y squared, which of course is 0, everything's 0 there. And then when you're going, and y is 0 too, so everything's 0 there. But then as you're increasing, it's a very small coefficient there, so you have a really wide parabola, and they're getting smaller, more and more until they go to, at the end, it's just going to be the z is equal to y squared. So that's your regular old parabola there, and it's just gradually getting bigger, and this way too. The picture doesn't show that very well, but who cares? Everything that's on the negative side of x is negative, everything there is positive, and they're exactly symmetric with each other. So the total volume, the sign volume, is 0. So why did they, I want to say waste my time, but it's not really a waste. Okay. Yeah.
I have a small question. The previous example.
Right.
So.
That one?
Yeah. No.
Before that?
Yeah. So.
That one?
We have x in there, so we just take the entire derivatives of only the y part, right? We just
Okay.
take the x and then we take the x later.
Okay. Now, yeah. The dA is made up of, that's not this return. Okay, that's the dx and dy. You can do them in either order you want to. Okay. Since the function that we're going to be doing depended on y alone, there's no x in there, let's integrate out the y first. So the previous one I did dx dy, who cared? It was x times y. It didn't matter which one you do. But this one, it does matter a little bit, but not too much. It just makes life a little easier if you do the y's first and then the x at the end. The dA is still dx dy or dy dx. That's the same. Okay? So we are integrating the y's first. So since the integrating y first, you make sure the inner integral is your limits on y, and the outer integral is your limits on x. Whatever your variable is there, that's what determines the limits here. And I chose to do this, so these would be all y's, and when you evaluated it, all the y's disappeared, and you just got a number here.
If we have an x in there, imagine like 8x.
Okay, if this had been 8x minus 2y?
Yeah.
Okay, then the 8x is just counted like a variable. That would have been 8xy if you integrate it this way. And then that would have still been a y squared. In that case, you had no advantage in doing dy first and dy second. You could do them either way you want to. You could have switched them, and if you had switched them and done the dx first, and this was 8x, then that would have been 4x squared minus 2xy. Okay, but then you evaluate only on the y part, the x's stay in there, so when you get down to this step, there's still an x in there, and then you integrate it out. Okay? Good question. you're looking way ahead, okay? And we were there. But that's good. I'm glad you brought us back there. Okay. Now, here we have what they call iterated integrals. Our main tool for evaluating double integrals is the fundamental theorem of calculus, okay? As in the single variable case, you use the fundamental theorem of calculus, we express double integrals as an iterated integral, which is an expression of the form. This is what I've already been doing. So that would be this. Integral from a to b times the integral of c to d of f of xy. And then which one goes first? In this case, dy, c to d of the limits on y, and then outside the parentheses is the dx. That's what we mean by an iterated integral. You do one integral on the inside and then the other on the outside, okay? Now, if that function really had x's and y's in there, you're only integrating out the y's on the middle, on this part. All the x's stay in there and wind up out here to be integrated later, okay? And if you flip them around, we do it. We'll get to that in just a second. Okay, so we first do, this is a weird way of saying, but they take this and call this some function of x, okay, s of x. Because you see, when you do this, whatever this function is, you're going to integrate with respect to y, so you fill in with the y's, then you're going to put these values in for y, so y's go out. So all that's left here is some value, they call it the function s, and the only variable you're going to have left in x. And then you'll integrate that out in the next one, and then you'll come up with an answer. Okay. And that's what they're saying. So let's do example 4. Now, oops. Here's what I meant to do. Okay, example 4. Evaluate this. The integral from 2 to 4, integral from 1 to 9, y(e) to the x, dy dx. Now they put parentheses in there. I say, let you put parentheses in there. What is the 1 to 9 representing? The limits on the y. It's going from 1 to 9. Y equal 1 to y equal 9. If you need to write that in there, write it in there to remind yourself. These are y's here. Y equal 1 to y equal 9. And on the outer ones, you can put x equal 2 to x equal 4. If you need to do that, do it. Just so you keep it in mind. You do, and we always do the inner one first. So they put it in parentheses. I'm going to put a circle around it. So the 2 to 4 stays where it is. The dx stays where it is. Let's do the integral in here. What does that become? Antiderivative of y(e) to the x dy. Guess what? We treat the e to the x as if it's a constant. So bring that constant out here and leave it here. That's got only x's in it. Leave it out there, okay? Now we've got the integral. So basically I take that and move it out here. So it's no longer here. So now it's just the integral of y dy. Y squared over 2 evaluated from 1 to 9. Okay? Now you tell me what that is. So this produces the integral from 2 to 4. Now, e to the x, that stays in there, don't worry about it. What's the evaluation of that? Okay, 81 over 2 minus 1/2, which would be 80 over 2, which would be 40. And that's a constant, so I can bring that out. That would be 40 times the integral from 2 to 4 of e to the x dx. And what's the antiderivative of e to the x? E to the x. I like that, okay? Evaluate it from 2 to 4. 4. And what would that be? 40 times. This I don't like as much, but it's okay. E to the 4th minus e squared. Is there any handy-dandy little form that's going to help us with that? Absolutely not. Okay, it's just evaluate it. Okay? So that'll give you an approximate answer, but it's 40 times that. Now let's see how they ended that. Yeah, that's how they leave it. 40 times e to the 4th minus e squared. If you want to evaluate it, evaluate it. I don't care. You know, it's fine. Now, sometimes for clarity, as on the right-hand side here, we include the variable in the limits of integration. Okay. So let's do example 5. Any questions on that one? Okay, example 5. Evaluate this. Integral from 0 to 4. Oh, notice they put y equals 0 to 4. You don't have to put it in both places. I sort of like to, but never mind. And integral from x equals 0 to 3. That looks sort of familiar, doesn't it? Okay. Of dx dy over the square root of 3x plus 4y. Okay. So you don't have to put the dx dy at the end. You can put it as part of the integral. But the order still matters. If you're integrating first with respect, inner is going to be the x, be sure you write the dx first. Yeah. And frankly, I wouldn't write it that way. I'd at least have the dy on the outside so I could separate them. So I'm going to separate them this way, okay? Now, how would you do something like that? Any ideas? Even if they don't work, what's an idea?
Let's change the square root to 1 over 2, and then since it's on the bottom.
Okay. I certainly like that idea. So let's see if that helps us any. And I'm going to rewrite this a little bit. Okay, it's the integral from y equals 0 to 4. Since they wrote it that way, I will too. Times the integral from x equals 0 to 3. And I'll leave my dx here. Well, let's do more precisely what you said. Okay. Okay, this is what I understood you to say. 3x plus 4y to the minus 1/2. Is that what you said? I thought that's what you said. Okay. Then do dx and then do dy. Okay. I like your thinking on that. What next? Say that? Go ahead. Try it. We'll see if it works. Say that again. Antiderivative of that thing. Okay. Is this what you're saying? 3x plus 4y to the 1/2? That would be part of it, wouldn't it? Over, okay. Is it over 2 or times 2? I think it's times 2, isn't it? It's over 1/2, which is times 2. Okay? Right? Now, if you don't believe me, take the derivative. 1/2 times 2 is this, and that's minus 1/2. That's part's okay, except we got one other thing to worry with. Sort of your anti-chain rule thing. So what do we got to do? Okay. Okay. You know a 3's involved, right? Because guess what? We're not worrying about the y. That's constant. So you're only worrying about the x. So there's a 3 involved, and if I'm not mistaken, it has to be down here. And again, how can you check that? Well, take a derivative of this thing. 1/2 times 2 is going to be, so you're going to have the 3 down here. This thing is the minus 1/2, sure enough. Then chain rule, take the derivative of this, which is 3. And they go out. They're dating. No problem. Okay. So, all right. So, I think that's it, isn't it? Yay or nay? 4y is a constant. It's a number. That would be like 3x plus 7 to the negative 1/2. You never use a 7, do you? Except when you're evaluating it. It's a constant. Leave it alone. Stay away from it. Okay. Only figuring with the x. Okay? So this, then, we're evaluating from x equals 0 to 3. Okay, I'm even going to write it there. And the dy stays here. See, what we're doing is this one first. Okay? And guess what? That 2/3, we're not going to use anyway. Let's put it to the outside. It's a constant. Get it on the outside so you don't have to mess with it anymore until the end. Okay. So now let's evaluate that. That's going to be 2/3. Let's leave the integral there. Y equals 0 to 4. Okay. Now we're going to plug in x equals 3. Going to leave the 4y alone. That's a constant. Leave it alone. Don't touch it. And that will be what? 9 plus 4y to the 1/2. Right? Minus. Remember, you got a minus in here. 4y to the 1/2. That's when you plug 0 in. Okay? Now, and this is all dy. See, the x's are gone, but not forgotten. Yeah, forgotten too. Okay. They're out of there. Okay? Now you got 2 integrals to do. Ooh, yes. But it's not too bad, I don't think. What about the first one? Now remember, the 2/3 is still there, so don't lose it. 2/3. All right. Now let's just do 2 integrals. Are you okay with that? The 2/3 have to be in front of each of them. Okay. That first one. Okay. That's going to be 9 plus 4y to the antiderivative. 3/2, okay. Over 3/2, right? Which is actually times the 2/3, right? Except we also have the unchain rule of the 4y, and that's going to have a 4 down here too, right? Okay. Now, I hope you won't get too confused here. I see a 4 up here and a 4 down there, so I'm going to get rid of them, so I don't have to mess with it. So it's just a 1/9 on the bottom. But this is going to be evaluated from 0 to 4. Okay, let's do that next one. 2/3. Well, actually, wait. Square root of 4 is 2 here, right? So let's just make that a 4/3. Are you okay with that? Let's take, okay. I know I'm cheating a little bit. The square root, this is a square root. This whole thing is a square root. Square root of 4 is 2. So 2 times 2 is 4, okay? And that just leaves us a y to the 1/2 here. See, that's come outside, okay, and become a 4. Okay, and what's the antiderivative of y to the 1/2? Three halves, which would then put a second over 3/2, which is the same as times 2/3. Okay, and this time there's nothing else to go. And let's say by pulling the square root of 4, which is a 2, out, you don't have any unchain rule to do, anti-chain rule type thing. It's out of there. We'll evaluate this from 0 to 4. I forgot to put the limits in there. 0 to 4. Okay? I think we can do that one. Okay, well, let's do both of them. Okay. The first one wound up being a, in the numerator, 9 plus 16 to the 3/2 power over 9. Do you buy that? Minus, just because it's a 0 there, you can't throw it away. What are you left with? When you put in the 0 there, it's 9 to the 3/2 power over 9. You buy that? Okay. Minus. Okay. The 4/3 I'm just going to write down. Okay. Oh, wait. Let's just go on and include the other. Let's make that 8/9, okay? Are y'all okay with that? I'm multiplying the 2/3 here by the 4/3 there. That gives me 8/9. So just worry with the y. You okay with that? Okay. And then this is going to be times. See, I pulled all these out. Okay, what is that? 4 to the 3/2 power. I can do the 0. Okay, done. Right? 0 to the 3/2 is 0. All right. Now, go move up to this white space to do. What's 9 plus 16? 25 to the 3/2 power over 9 minus. Does anyone know what 9 to the 3/2 power is? How about 9 to the 1/2 power? What does that mean? 3. And 3 cubed is? 27. That's what it is. Over 9. Right? Minus 8/9 times, what's 4 to the 3/2 power? How about 4 to the 1/2 power? Ah, this is 8. Okay. Okay. How about 25 to the 3/2 power? 125. 125/9 minus 27. Well, let's just add. Okay, let's 27/9 minus 64/9. So 27 and 64, I believe, is 91. Is that right? 91/9. 91 from 125 would be 34/9. So I hope the answer is 34/9. Yes, thank you so much. Okay. That's what we got. You see how that works? Now, there were I did some manipulation with the numbers, but that was all legal. If you have numbers, get them on the outside. Just don't forget to put them everywhere they need to be, like the 2/3 need to be in front of both integrals. And the 2/3 here, and you can do the things here. So Be sure you keep up with everything, but if you do, it works out pretty well. Yes.
If you integrate, integrate them both and then leave the 2/3 at the outside and then multiply the 2/3 at the very end, would that work, or would that?
I think so. Yeah, it would. Yeah. Yeah, that's definitely doable. Definitely doable. Can't look there and tell you what it would be, but yeah, that would have been a 25. The 2/3 right here would be a 3/2 basically with that. Yeah. So yeah. And it may have made it easier. I don't know. That was example 5. They want us to go to example 6, and there's no slide for that, so let's erase all that we have here.
Are you going to give us the test?
What's that?
Are you going to give us the test?
Yes. Is it time? Is it past time? Oh, okay. What time is it supposed to? Okay. Yeah, we stop at 1:40, right? Okay. Let's try to get one more in, okay? We don't want to lose anything. Okay. So, it's a okay? I wish I hadn't have erased that. It just says what happens is we reverse those. And this time did the y's first. Y's last, y equals 0 to 4, because we did it the other way first. No, we'll do it the x equals 0 to 3, and then the y equals 0 to 4. And we'll do the same thing. This time it'll be dy dx over the square root of 3x plus 4y. So we've already done the other way, so we want to do it this way. Okay? Now, I am doing it right. Yeah, right. Okay. Doing this one first, and of course I'm sure that Emmanuel will want to write that as 3x plus 4y to the negative 1/2. You integrate that first with respect to y. What will that be? So the x's are going to stay here. X equals 0 to 3. And this will be be 3x plus 4y to the 1/2. That'll need a 2 out front, so I'm going to put it all the way out. And then we're going to have a divided by, since you're integrating with respect to y first, I'll have a 4 here. So that's going to make that a 1/2 there. Okay? I think that's it. Evaluated from 0 to 4. Y equals 0 to 4. So we got to evaluate that first and then do the dx. You following this okay? So 1/2, the integral from x equals 0 to 3. Okay, my writing stinks, but forget that. This will be 3x plus, plug in the y, 16, right? 4 times, yeah, 16 to the 1/2 power minus 3x to the 1/2 power, right? And this is times dx, okay? Now again, you may want to do your integrals second. This time we'll leave the 1/2 on the outside because Emmanuel insisted we do so. X equals 0 to 3. Okay, can we do that one? be your antiderivative of that. Antiderivative of that. To the 3/2 power times 2/3. See, I want so badly to cancel out those 2's, but man, it won't let me. Okay. And that's going to be evaluated from 0 to 3. Okay. Minus. This time I'm going to pull that one out because it's no problem.
What about the 3x plus 16? We don't do the chain.
The what?
The inside of this curve. 3x plus 16.
Okay.
Would we divide by 3?
Yeah. Oh, yeah. Okay. Divided by another 3. You're right. Okay, got it. Yeah, good catch. I pulled this 3 out so we wouldn't have to. I was thinking of doing that. Okay, what's next? X to the 3/2 times 2 over 3. So the 3 goes and that's off with a 2, right? And that's evaluated from 0 to 3. Okay? Let's see. 1/2 times all that, because manual won't let me. Okay? And that will be 2/9 times 25 to the 3/2, which is 125. Okay. Minus x equals 0 here would be 2/9 times 16 to the 3/2, which would be, second? 6, okay, to the 3/2. I'd like, yeah, 64. Okay, I couldn't hear what you said. Okay. Then it dawned on me you were saying 64. Okay, got it. And then we have a minus 2. What's 3 to the 3/2? 27. And the 0 I can do. Okay. Now, Emmanuel, can I please get rid of the 2's now? Okay, that go away. Okay. Whew. Okay, you're a tough taskmaster. And what do we get? 125/9 minus 64/9 minus 27. Isn't that just what we had before? I think I erased it all. But wasn't it the same thing? Okay. Guess what this indicates? This indicates Fubini was right, doesn't it? That the double integral of a continuous function f of xy over a rectangle R, which is AB. What does AB represent? X, the limits on X, by CD, which represents the Y's. Yeah, that's what Y is going to say. Is equal to the iterated integral in either order of that. Either do the Y's first, y equals integral of y equals c to d of f of xy dy, do that first, and then do, when you plug in the y values there and get rid of them so you only have a function of x left, then do the integral of that function with respect to x and integrate that a to b, and you'll get rid of those two. Or you can do it the other way, integrating x a to b first with a dx inside, and then that'll give you a function of y, and then give you the other. Okay. Sorry we didn't quite get to finish, did we? Boo, yes. Okay. I've got one little thing to do. I told you this at the beginning. You were in here. The secretary left the finals to be copied last night, and when I came in this morning, she hadn't finished copying them, and I haven't been back since. So if you'll hang on for just a minute. Any questions before I end the recording?